morning here. In any event, my name is Shelley Sharma, and I'm from the sales group here at GL. I'd like to welcome you to today's GL webinar, which focuses on our ED-137B tools for VoIP-based communications for both ground-to-ground and air-to-ground communications. Matt Yost and Srinivas Balulad will start the presentation momentarily. I want to take just a quick moment to touch base with you on the ATM World Congress show in Madrid, which is rapidly approaching. I think it's being held early next month. I guess the dates are 7 March to the 9th of March. While we don't have a booth at the show this year, I will be there meeting our customers and our would-be customers. If you are going to be there, then I'd be happy to meet with you. If this is agreeable, please let me know via email or by phone. My email address is very easy. It's simply info@gl.com. I look forward to hearing from you and possibly meeting you in Madrid. When you contact me, please be sure to provide your cell phone number so that we can make last-minute adjustments to whatever we arrange, just in case that becomes necessary. I hope to hear from you soon, and I look forward to seeing you in Madrid. With that, I am turning the webinar over to Matt and Srinivas. Matt?
Okay, thank you. Thank you, Shelley. Again, my name is Matt Yost, and I'll be joined here by Srinivas, and we're going to administer the webinar this morning. Welcome again to the webinar on our test tools for ED-137 in the arena of air traffic control and air traffic management. So GL Communications, if you're not familiar with us, we're a United States-based company. We're in Gaithersburg, Maryland. We also have offices in Bangalore, India, and in China, Shanghai, China. We have representatives around the world. We were founded in 1986, so we've been around for a little while. There are basically two main divisions here at GL Communications. One of them is kind of strictly consulting services, engineering consulting services, and we do that for a variety of local and state, federal governments, as well as private sector companies. And the other division at GL is our test and measurement equipment division. So we provide test equipment through our reps, through sales directly. All of it is in-house, homegrown, designed from A to Z. Hardware, software designed, and it addresses, all of the networks and all of the different equipments and so forth across the telecommunication industry. We kind of specialize in PC-based test equipment, so with that fact, everything is visual, and we can store to hard drives, things like that, and we're portable in nature. So the next slide is devoted to, really, it's sort of a funny way to discuss the webinar agenda here with a network diagram, but this is a typical air traffic control or air traffic management network diagram. And the reason I put this up here is to just talk about this webinar and how we're going to sort of break it up, what the agenda is for the webinar. Basically, the first portion of our webinar is going to be devoted to what we're showing in the picture here, called MAPS, and MAPS stands for Message Automation and Protocol Simulation, and that is our protocol simulator to simulate ED-137, the SIP protocol, in a bulk calling fashion and in a single calling fashion. There's a lot of flexible options with that product. We'll get into a little bit more. A subsection of that area of this presentation or this webinar will be about our recent enhancements to that product. That product's been out there for a little while now. It's gained some traction in the community, and now we're going to address some recent enhancements to the product. Second section of our webinar is a short section, but it'll be devoted to, in our diagram here, if we can show the packet scan down at the bottom right of the diagram, and what we're calling our Net Surveyor web. So these are non-intrusive monitoring testing tools that we have, similar to Wireshark, if you're familiar with that, but a lot more advanced than that as far as the traffic analysis and so forth. And then the third and last thing we want to talk to you about is something that is very important in this environment, and that is delay measurements throughout this network. GL has put together a suite of testing tools that provide access to all points along the network path via the 4-wire analog point, maybe right at the controller position, working position, any IP point along the way, 4-wire circuits that may be in there that are legacy circuits. So we've got tools in place to monitor those different places and in fact inject audio and do different things, all centered around doing delay measurements. Okay, so precise delay measurements. You can do precise delay measurements. And so that'll be the last thing we talk about today. Everything is in this format, in this webinar format, is fairly overviewish in nature. So I recommend that you follow up with us if you need some more explanation on exactly how we're accomplishing some of these things. But we're going to kind of focus on sort of the applications during this webinar. So with that, the first section we'll get into here again is our protocol simulation section, and that again is called MAPS. I'm going to, Srinivas, my colleague here, will be taking over and doing this section, and I will join back in again for section number 2. So with that, Srinivas.
Yeah, thanks, Matt. Hello, everybody. Now I will present our MAPS radio and telephone emulators. Before beginning, I would just like to introduce about what is this MAPS. MAPS stands for Message Automation and Protocol Simulation. Okay, MAPS is our standard framework to simulate a wide range of protocols across TDM, VoIP, and wireless technologies. As the name suggests, it provides the complete control over defining the message content and also the protocol state machines. So that is the biggest advantage of this architecture. Now I'll begin with ED-137 telephone emulator. It's a lightweight software only, and it has a very user-friendly graphical interface. Okay, and it also has an incredibly flexible architecture that allows user to have custom test scenarios. So in the next slide, we'll be seeing the highlights about this ED-137 telephone emulator. So basically, it emulates CWPs as per ED-137B volume 2 telephone interface at the controller working positions. Okay, hundreds of CWPs can be simulated in a single instance of MAPS telephone, and each simulated CWP can have a unique IP address also, so that something to simulate it is located in a different geographical location kind of thing. Okay. Next, the supported codecs include like G711 A-Law, U-Law, and G729, and we support like different traffic actions on the call. Basically, send and record audio to file, send and detect digits and tones, and we can also send the live speech using the microphone or play the voice on the call using the speaker. We can simulate hundreds of calls to perform load generation and also like background traffic generation also. It is not just like a single call emulator, so it can generate the load. It can be used to generate the load also, so that we can conduct the load testing on the DUT or the network under test. Continuing with the features, these are the 8 call types defined as per the ED-137B volume 2. So you can see here all these instantaneous priority calls and monitoring calls, basically 3 types. Okay, and along with that, for each call, we'll be providing a ladder diagram. I mean the message sequence diagram indicating the message flows and also along with the timestamps. And we also provide the message decodes for each of the call, each of the message. So with this, these are the important features of telephone emulator. Now I will move on to the radio emulator. Basically, a MAPS radio emulator, it is again like telephone. It is a lightweight software only, and it has a very user-friendly graphical interface. And it also provides a flexible architecture that can help the user to simulate his own custom test scenarios. So continuing with the highlights of this radio emulator, basically it emulates the ED-137B radio interfaces at CWP and GRS nodes. So you can see here, MAPS radio is being used as a CWP here, and the same MAPS radio is being used as a GRS. So it can act as either CWP or a GRS. It simulates all the radio call types, basically like radio TX-RX coupling, receive only and idle calls, and it also supports all the PTT types like priority, emergency, normal, and coupling calls. It can also simulate radio remote control equipment to handle the radio remote to radio control commands also. Okay. So in the next slide, you are seeing the radio profile here. So you can see here some 10 radio profiles have been defined. Each profile will represent one radio. Okay, and each one will have its own parameters. Basically, what is the radio emulation type, unique frequency IDs, and also unique IP addresses, and other parameters like what is permitted users and all. And apart from this, it also supports like WG67 key-in event, call preemptions, and permitted user lists, restricting the permitted user lists. Additional feature-specific RTP header extensions like climax time delay, radio remote control, and signaling quality indexes are also supported by this radio. And we can also apply the impairments. Basically, these are like packet loss, packet effects, which includes like generating duplicate and out of order packets. And we can also apply the latency in the generated RTP traffic. So this will help in testing your network or device under test to know how it can cope up. In the next slide, this is the call reception window. Okay, basically you can see here there are 3 radios, and each one of them have a multiple A to ground calls. Okay, and they are also represented using different color codes to just to make the visibility clear. Okay, and this is the event buttons. Okay, which can be applied on the call. Okay, basically these event buttons include like start the squelch action, or it can put the radio in summation mode, PTTS, or apply the SQI values. Okay. And apart from that, it also provides the message sequence along with all the radio events that are happening on the call, along with the timestamps. So you can see here there is an emergency PTT on. And apart from that, each message decode is also provided on the right side of this. Now, recently we have made this release of this ED-137 Radio emulator, and this involves some important enhancements, basically like multiple radio simulation within a single instance of MAPS radio, and IP address spoofing, which is used to simulate multiple controller working positions or radios with unique IP addresses. And the third one is link session management. Okay, and this link session management will actually allow the radio to group the calls coming from the same user part, but with from different devices, essentially from different IP addresses into a single logical session to a radio. And advantage of this link session management will be like it helps in providing a higher service availability and handles redundant connections to the radio. Means it will radio will have the capability to terminate the calls, redundant calls. The other things include some of the additional user events. The one is like sending re-invite to update a SIP existing SIP call. For example, some good examples will be like I want to convert a radio idle call from call to a radio TXRX call, or I want to change the codec from ALO to G729, something like this. And received traffic. So basically, it will allow the user to either record the voice on the call, to a file, or it will allow the user to detect the digits and tones on the call. And next one is we are handling the PTT priorities at radio when the radio is in PTT lockout mode. So in the next slide, we are pictorially trying to represent how the concept of multi-radio simulation. So you can see here we are simulating 3 radios using a single MAPS radio, and each of these radios can be emulated as either as a transceiver, receiver, or a transmitter, and each one can have its own frequency and also a unique IP addresses also. At the other end, similar to radio, like this MAPS radio is being used as a CWP, so it is simulating multiple controller working positions in a single instance. So you can see here, these controllers are multiple controllers are connected to other end radios. Next one is the linked session management feature. So you can see here basically this radio has the link session management enabled. Okay, in that case, the calls coming from the different devices, basically they'll be having different IP addresses, but they'll all be having the same user part. And along with these things, it will also have the linked session parameters included in the SDP. So when this radio detects calls coming from a same user part, it will group them and treat it as a single logical session to the radio. And along with linked sessions, it can have other non-linked sessions also. I mean the independent sessions which are not part of the link session also. Now we'll move to the live demo of our recent enhancements.
Now we'll demonstrate the multi-radio simulation feature. I'm using Remote Desktop Manager to control 2 systems here. In the first system, I am using MAPS radio to simulate 15 controller working positions, and in another system, I am using MAPS radio to simulate 3 radios here. And out of these 3 radios, I have configured first as a trans receiver, and second as a transmitter, and third as a receiver. And each of them will have a unique frequency ID, and also they will be having a unique IP addresses. Okay. Now we'll try to place the calls from other end CWPs to these radios. So you can see here 15 controller working positions have been created. The first 1 to 5 CWP will place call to the first radio. 6 to 10 will place call to the second radio, and 11 to 15 will place call to the GRS3. We'll go to the call generation window. Now you can see here I have 15 entries here. I'm using 15 CWPs. Now we'll try to place the call to the other end radios. So you can see here all the calls have been established. If you check at the other end, okay, so there are 2 calls each of these radios. So you can see here we are using the different color codes to represent the calls to a particular radio, and we are also trying to group them so that identifying calls to a radio becomes much easier. Okay, if I go back to the CWP end, I can try establishing more number of calls. Okay, so I have placed 4 calls to the first radio. Okay, now I'll do a key PTT on the first call. Okay, so you can see here the normal PTT is sent, and there is an acknowledgement from the radio. the same thing will be reflected on all the other connected calls. Now when I do the emergency PTT, this will override the normal PTT. So you can see here emergency PTT is on now. Same will be indicated on all the other radios. Okay. So this is just a brief introduction about like how we can demonstrate, how we can simulate multiple radios here. Now we will demonstrate the link session management feature. At the CWP end, I have created CWPs. One is main CWP and a standby CWP. Both have the same user part, but with different IP addresses, and both will be placing call to a same radio. So you can observe here, and both will have all the link session parameters enabled also. Okay. Now on the first radio, I am placing the calls, and I have enabled the link session management feature here. Now we are ready to receive the calls. I placed a call from main CWP. This is acting as a radio TXRX connection. This is the active session within this for this radio. And from the standby CWP, I am establishing a radio idle session so that this session is reserved for in case main CWP goes down. Okay. Now, say for example, from the main CWP, we are not hearing the voice properly, and I want to use the standby CWP. For that one, what we'll be doing is go to the profile editor, make the standby CWP from radio idle to the radio TXRX, and also change the link session parameter from keep ls to delete ls. This parameter is going to instruct the radio to terminate the unused sessions. For example, once we switch to main standby CWP, main CWP session will become redundant. That will be terminated by the radio. So now on the second session, I'm going to generate a re-invite here. Okay. So as soon as I generated a re-invite, now this has become an active session, and you can see the first session, which was a main CWP, has got terminated with the reason link session clear command. This is all about link session management.
Okay. Thank you, Srinivas, for that. The updates on ED-137, the MAPS product from GL. This section of the webinar is devoted to GL's monitoring solutions. So these are the non-intrusive monitoring solutions from GL in this air traffic control environment. Again, what we have there, if you're not familiar with our products, we have a product we call Packet Scan and another product that's referred to as Net Surveyor Web. These products work in conjunction with each other. Packet Scan can definitely work on its own. Packet Scan is more of an IP sniffer, similar in nature to Wireshark. It will do all of the protocol decodes. It will, in ED-137, it will allow for the extended header to be seen. But where it really shines is with its traffic analysis. Okay, so we're able to do, if you're familiar with ED-138, we're able to do a lot of the statistics outlined in ED-138 with Packet Scan, and we'll show you those here briefly. So again, a PC-based product. Packet Scan is a software-only product. You can install it on a laptop or a rack PC in your lab, or it can be deployed in the network somewhere and essentially report back to you statistics and so forth, which I'll show you. So Packet Scan, again, interfaces directly to your network. This is a simple diagram to show that Packet Scan in an air traffic control or air traffic management network can be deployed at multiple locations. Okay, so at Site 1, we can have Packet Scan monitoring the activity. Same thing can be done at Site 2 and at Site 3. Okay, and this can be replicated across your network at strategic locations. These packet scans, again, can operate solo in nature, so they you can have a technician deployed to a site of interest where maybe some problems are happening or you're turning up a service or something, and packet scan can be used as a troubleshooting tool just to see what's going on, to evaluate the network, to investigate the traffic, and so forth. What it can do as well, what I just described was sort of in a troubleshooting mode or in a discovery mode of what's going on at on a particular node of your network, or maybe you're trying to evaluate a particular piece of equipment in your lab. It's great for that sort of lab environment troubleshooting tool. But what it also can do is it can be deployed in the network unaccompanied by a person, and after it's set up and monitoring at a strategic location, it can report all of the statistics back down to what we'll call a central database system. And multiple of these packet scans can be doing that. So this architecture shows you that multiple packet scans can be deployed in your network. They can all be sending statistics, and when I talk about statistics, I will show you a little bit about that, but essentially call detailed records kind of starts it off. And so the information about the setup for the ground-to-ground calls will all be there. The PTT, the squelch break exchanges from the air-to-ground calls will all be there. And then statistics can be derived from that, as well as now looking actually into the traffic. So when people are talking, the voice traffic, we're monitoring for the quality of service of that. So we're able to give a MOS score. We're able to provide the jitter for those sessions and so forth. So all of that information can be stored in this particular architecture with NetSurveyor Web at a database. And then that is accessible through a browser. Okay, so there's a web server sitting there sort of mining the database, and then that is accessible through a web browser. And that can be locked down to only people on site, or it can be made available to anyone, at any browser, anywhere. So I mean, in this environment, obviously that may not be the case, but you can secure it in any normal way that you would provide network security to a web server. So I'll focus a little bit quickly on packet scan and what it offers. Packet scan, again, is a network sniffer, GL's network sniffer, and it can be a lab tool, or it can be deployed in your network and sit there without interaction, doing its job. It's really broken up into two different views. Okay, one of them is what we're showing here, which is the protocol decode view. This is similar. I'm sure most of you are probably aware of Wireshark. This is similar to that. So it shows you every packet going by, and you can see that here being captured. With whichever one is highlighted, you're seeing the sort of plain English decode of that packet. So you're getting that. You have the hex dump. You have all of that nitty-gritty information with this in the protocol decode view. We've got all the traditional advantages to how these sniffers work with filters. You can filter in and out different traffic when you set it up to start capturing. We do, in this ED-137 environment, we are decoding the RTB header extension field. So all of that is there, and you can see in this particular screenshot, this is an RTP keep alive packet, and you can see the extended header here, where the PTT is off at the moment. So we're showing all of that information. I think this is a fairly common, a Wireshark type view. And what I had mentioned earlier, where we feel this product shines is on the traffic analyzer view. So what happens here is all of these packets are being captured, non-intrusively being captured at a strategic point in your network or in your lab, and we're able to, with this traffic analyzer, we're able to organize those into some logical manner. Okay, that's per call basis or per session basis in this environment, and we're actually able to show you both directions of that particular session or call. and with all types of normal VoIP type statistics when we're talking about voice. They're defined in the ED-138 spec there. The statistics, you know, some of them are MOS, the R factor, and the packet loss, delay, and the jitter. So we're showing all of that, as well as many other things that we have. And what you can see with this view is it's providing sort of an aggregated view of the network. So whichever point that I'm particularly monitoring at this point, I'm seeing multiple sessions or calls. And I can obviously look at them in a holistic view with a lot of statistics down here on your particular capture point at that packet scan. What I can also do is, as well as, you know, before I jump ahead, as well as I can select one of interest. It will show you the message sequence ladder diagram as well as the decode of each one of the messages that are on there. So you're getting that information as well. If your heart desires, you can listen to that call in real time. Okay, so through the speakers on the PC that has packet scan on it, you can be listening to that call or that session. So if you're monitoring a CWP to radio session, you know, whenever the controller hits PTT, you're going to hear it. You're going to see it. You're going to hear it. You're going to see the statistics of that particular thing. When squelch break happens from the radio end back down, you're going to see it, you're going to hear it, you can monitor that. Additionally, we have a view where you can select one of these sessions or calls, and you can click this button here, which will zero in even deeper on that particular session. Okay, and in that manner, what we can do is show you in real time. We can show you things like the oscilloscope or a spectral display of the voice. Again, we'll show you jitter graphs in real time as things are happening in real time, MOS graphs as they're happening in real time. So that's after you've zeroed in on one of interest. Okay, so it's a very good troubleshooting tool. It's a very good network turn-up tool to make sure things are working, everything is okay. So I'll just leave it at that for now. One other thing we can do, even at the packet scan level, at the, we'll call it the probe level, is we can set it up to trigger and do something off of a trigger. For instance, if your conversational MOS value goes below a certain point, I want to start now recording to the hard drive that particular session, so that I could possibly go back and evaluate it later. So there's some built-in things of that nature, so we can trigger on different things. You know, you can dream up the scenarios, and then you can start acting on those things. You can log different events. You can start recording voice. You can do those types of things. Back to the simple diagram of the network architecture. What we just saw was everything at the interface level here at the packet scan. What I mentioned earlier is packet scan can push statistics down to a database, and that's what I'll show you now very briefly. This Net Surveyor web is now the database view of all of your packet scan probes in your network. So if you have an opportunity, if you have a need for monitoring at a lot of different points, this web server view allows the aggregation of all of those probes and then the viewing of all of those statistics and all of those calls and so forth. So it allows bringing together multiple packet scans to a single place. And there's a lot of nice things built around it, like the generations of reports and definitely alarms. So all of the same type of functionality that we mentioned before can be done here. And I'll move along. You can see here, there's one example where we're monitoring over time or per day the conversational MOS, so the MOS scores and the packet loss. So we have a lot of built-in, you know, right off of the shelf graphs and statistics. Everything within this environment is easily manipulated and configured. It's all SQL based, so we can dream up, and the customers can dream up scenarios that, hey, I want to see this broken down into, you know, X, Y, and Z. Well, that's all very easily done. We can write a very short SQL statement, and then a graph, a customized graph, will appear for you. So, on top of that, you know, at the Net Surveyor web level, so at the aggregate level where multiple packet scans are feeding it, we have the ability at that level, so we're watching the whole network, multiple nodes, we're able to trigger on different thresholds or a call of interest, time of day met maybe. So there's a lot of different trigger events that you can build into this thing. So for instance, as I mentioned earlier, a MOS score goes below a certain point on your entire network. I want to see that. I want to log that. I want to throw an alarm. I want to get an email about that. Those things can happen. So that would be the action of the trigger. So, for instance, in this particular case, as we know in ED-137, an air to ground SIP, we'll call it the SIP portion of that, is tied up early, day one, and then it stays up. If something would change in that at the SIP level, somebody would want to know about it most likely. So we can trigger on those types of things, and then you know, provide alarms and give an action, an email to a network administrator. One other thing that we can do, and is shown in one of these this screenshot here, is let's say every night at midnight you just want to get a report on the daily activities. We can set it up to work automatically, and can send you a graph. It can email you a chart, a graph, or whatever every night at midnight. So there's a lot of niceties built into after we have all the data collected, we can present it to you. Okay, as we're moving along here, I wanted to go into the third section, and we'll just kind of go right into it here because I want to get to this section of the webinar before we start questions, and I'll try to get through this in short order, but this particular section of the webinar does take some time to explain, but I'm going to highlight how GL is providing these time measurements within this air traffic management network, and that's what this section is devoted for, and we will take questions at the end of that. A very good diagram to kind of show this whole environment is this one. This simply shows at this point a working position. Okay, this diagram shows it going into a legacy VCS. This can obviously be an all VoIP VCS as well, and it doesn't matter to our test equipment at that point. I'll explain that shortly. We have what we have. Generally, this is broken down into three, I'll just call it three products from GL that sort of work in harmony. One of them is called an audio analyzer. That is a 4-wire audio analog interface point. It can interface to an existing CWP. It can control the CWP. It can press the PTT button. It can send audio into the CWP. It can record audio. It can do all of those types of things. So it's a 4-wire interface. We have access at that layer. We also have what we call a second key component to this whole thing is a packet analyzer. So a packet analyzer is an IP piece of hardware that can sit at some point in your network. Okay, it can be strategically located, and it basically is filtering on packets of interest and timing those things, okay, or forwarding them to a timer device. So each of these components, with the audio analyzer and with a packet analyzer, you can place these guys at any point in a network, an ATM network. Packet analyzer can be placed right in front of the radio. Another audio analyzer can be placed on the analog side of the radio. Okay, with those two products, we have access to all points. Even with legacy voice circuits, 4-wire legacy voice circuits, an audio analyzer can be placed in a sort of high impedance tap mode. Okay, so if there's a need to get a timing measurement at that point, we can do it. So these two products are the interfaces. Okay, so they are the on-network interface. They basically will do different things. For instance, intrusively, and in this case, non-intrusively. But everything is sent to a event data logger, we'll call it, and that is where the timestamp gets put on everything. Okay, all of this is done at the hardware level. So we're talking about like the FPGA hardware level here. No Windows is involved. No Windows latency is involved in any of what we're about to tell you. So I wanted to spend just a little bit of time on this to sort of introduce it. I'm going to have a slide or two on each one of these components so that you kind of understand what they do in a little bit more detail. But before I do that, just one scenario. Here's just a real-world scenario on what we can do. An audio analyzer can be hooked up to a CWP, a real-world CWP. It can, through software, it can, and through scripting and so forth, it can initiate a PTT session. Okay, when that PTT is actually done at the analog side of things, at the controller side of things, that can be sent back to this event data logger for a timestamp. Very quickly done, very precise. When the let's assume that this is now IP at this point, and we're talking ED-137. When the PTT on in the extended header shows up, our packet analyzer is watching that, again, at the hardware level. When it sees that, it sends that to the event data logger, and you can delta those two events. So we've got a system here, and we've got components where we can do delay, very precise delay measurements from an analog interface to an IP interface. Okay, and that's slightly uncommon in the world of test equipment. I mean, generally somebody's doing, you know, a delay measurement from analog all the way to analog. We've got this product in the middle here at the IP layer that can do those things, and you can dream up what the packet analyzer can be looking at in the ED-137 world. Okay, so PTT on is just one thing, squelch break. There's a zillion, the mute. All of the scenarios can be looked at and timed with this guy. So let me jump ahead. I'm going to just identify each of these products, these three products, in a little bit more detail now with a slide. The audio analyzer, again, homegrown hardware and software that GL has produced. It can, it sort of sits there and it acts like a controller. So it can start up PTT, and when it does these different things like PTT on, PTT off, start of audio, detecting of audio, it is basically sending a signal up to a timer that is timing those things, all of those events. As I was mentioning, can inject and record audio signals at the CWP and at the far end at maybe the radio interface. In addition to all of this timing measurements and delay measurements, it has the ability to send and record voice and audio. So we can do traditional sort of voice quality analysis using PESC or Polka. These are communications algorithms that are used throughout the industry to evaluate voice quality. We can do that. And there's a built-in GUI CLI that makes things very seamless if you want to integrate it into a third-party testing platform. The audio analyzer, just one more slide on that, can be set up. It's a 4-wire balanced audio device, so PTT contact closure built into the software can connect to the audio interface on a CWP. It has the ability, if you have some legacy traditional circuits that are out there, 4-wire circuits, it has the ability to go into a bridge mode. So it can be monitoring that 4-wire circuit and viewing different things related to the audio, when no audio is present, when audio is present. So those types of things can be timed as well. It can inject and record audio. It has, like I said, voice quality and one-way delay measurements, round-trip delay measurements, and so forth. So the diagram here shows it at different places, but as I was saying, at 4 wire locations throughout the network it can be placed. So it doesn't matter that necessarily that the VCS, the CWP, is a legacy one or it's an all ED-137 CWP. It doesn't matter to us because we're going to be on the analog side of things with this product. Back to our main diagram that sort of showed you about this guy and this guy, same thing. Now I'm going to show you a little bit about this packet analyzer, which is sitting on the IP side. Again, it's a homegrown GL product designed from scratch, from the ground up. It has a very complex packet filter, which I'll show you a little bit about. And when things of interest happen, when you've told it to look for something, it will trigger, and it will either filter that packet, store it, or it'll time it and send it on its way somewhere. So these things are to a central timing point. We can log events, and it's all done interface-wise through Windows, but all of the timing and the processing all takes place at the hardware level. So how this works is this packet analyzer, in this diagram here, you might have network A, we'll call it network A and network B, but at some point in your network, at the IP side of things, you're going to run packets essentially through from, let's say, port 2 to port 3 on our analyzer. So everything is flowing in both directions here, right, like that, through us. So we're monitoring everything, and we've now set up a filter to watch everything here. So we're looking for certain events. In the case I described earlier, we're looking for the PTT on bit, okay? When that happens, we see it, and then what we'll do is we will either start recording directly to a hard drive there, all the packets, or we can actually forward the packets out another port over to a timing device. Okay, we can actually create a pulse, okay, that you can hook up to an oscilloscope if you want. So you can time it in the lab. You can send it to an oscilloscope, and when that event happens, you'll see a rising edge on the oscilloscope. Okay, so there's a lot of ways we're doing that there. There's a couple different ways. But again, all of it's done at the hardware level, all of it's done at a very precise nature. So our filtering, it can be done at layer 2, layer 3, and layer 4. That's important to understand. And the depth of our filter, we're not going to get into exactly how the filter works, but from just an application perspective, you can be filtering on a certain byte in all of your IP packets. So again, the sky is kind of the limit there, and we've done a lot of different things with this. Okay, so let me move on slightly. The last thing that I want to talk about again is the packet analyzer and this audio analyzer are able to do an interface at these different, the IP layer, and now we're talking over here at the analog side. These things are sending whatever triggers and whatever events that they're responsible for back to an event data logger. Okay, this is actually where the timing gets placed on all of these events that are coming in, and this is the sort of central timer. Okay, so that event data logger, simple device. It's actually the exact same hardware as the packet analyzer, just a different load. Doing a slightly different thing. So it's, again, our GL homegrown hardware. And it provides, a very simple log file of the captured events. So you can tell the deltas between different events within your network, timing-wise, the delta times. And all of those things can be sent back to a user interface. Okay, we're actually using a version of our maps, which we showed earlier, to display these different timing events. So all of that is being reported to the user. So basically that is the components of how GL has accomplished doing these timing measurements within this environment. The one thing I'll sort of close on with that is, you know, if you're if you're responsible for the network, it becomes important to make sure that your time is good through your network at different points. If you're let's say you're a radio manufacturer, you can isolate obviously just the radio. With all of the products we've shown you today, we can put the packet analyzer right on the front end of the ED-137 entering the radio. And let's say we see the first, you know, audio packet going into the radio. Well, how long does that radio take to basically energize and throw out the audio on the RF side? You know, those types of measurements are all possible with these products. How long does it take when things are muted for the audio to actually stop? Okay, we can do that. We can measure those types of things. There's a lot of different tests like that that require timing that can be done. It can be done at a sort of a system network level. It can be with the products that can be placed on either side of a particular node of interest in the network. So that's kind of what I wanted to close on with that. And just sort of wanted to give you that overview on how these critical measurements are done. So at this point, that is all we have to present at the moment, and we thank you for attending. Hope this was helpful to you. Get a decent overview of how GL is doing some of these things. We're excited about this community. We think we have some good test equipment that can be applied in different areas to help out. Well, thank you, everyone, and if you're still on, thank you very much. If you need any follow-up, please again send us some emails or call us directly. Thanks for attending. Appreciate it. Bye.